Hello. So in this video, we're going to go over what are gravitational fields. So we're going to go over the first intro definition of what actually is a gravitational field. So gravitational field, if you look at your data sheet, you can see that G, which stands for our gravitational field strength, is equal to the force per unit mass. So again, gravitational field strength is the force per unit mass. So that's our definition. So what is gravitational field strength, or what is a gravitational field? It is going to be the force per unit mass. Okay, what a unit mass means just means like a 1 kilogram mass, basically, or a point mass. Okay, another equation you can see for G, which is our gravitational field strength on your data sheet, is equals to capital G times capital M divided by R squared. And it tells you you only ever use this one if it's a radial field. Right? So what is a radial field? So there's two ways to look at it. Okay, so we have the Earth. We know the Earth is spherical. And we know that because it's got a mass, anything with another mass, so let's say we got our point mass, that's 1 kilogram, we know that gravitational fields, they are always attractive. And because there's always attractive, that means that that 1 kilogram mass is going to get pulled towards the center of the Earth. So what we're saying is that 1 kilogram mass is going to follow this line. It's going to get pulled towards that center of the Earth. If I put 1 kilogram mass here, it's going to get pulled towards the center of the Earth. 1 kilogram mass here is going to get pulled towards the center of the Earth. So you can see this is what's like our radial field. It's like spokes on a tire. So our radial field. So what we're saying is any point is going to get pulled towards the center of the Earth. Okay. So because an attractive field, again, our G for our radial field shows us that we use G, which is our universal gravitational constant, and that number on your data sheet is just 6.67 times 10 to the negative 11, multiplied by capital M. Capital M is the big mass. In this case, it would be the mass of our Earth, divided by R squared. The distance is away from the Earth. So hopefully you can see for our radial field, the further we are away, the bigger the value of R is, the smaller the value of G is going to be. So for example, if we're a point up here, where that R is extremely far away, the value of G is going to be much lower than if we were here, where the value of R is much smaller. So this value of G here is going to be much higher. And we can also see that because, again, if you think about magnetic field lines, poles of a magnet, where they're more dense, more concentrated field lines, that's when you know the gravitational field is the strongest. However, roughly within the first 100 kilometers of the Earth's atmosphere, we can model it as a uniform field. So what that means, if this is the Earth, we can roughly model as that field lines as constant, uniform around the surface of the Earth. So again, what we can see it's uniform because we have parallel lines and we can see they're all equally spaced. And now we're going to say that G, our gravitational field strength, is equal to our force per unit mass, and it's going to be a constant for a uniform field. So again, for a uniform field, or what's going to say is that G is going to be a constant, there should be a constant gravitational force per unit mass pulling it towards the center of the Earth. Okay, but for a radial field, we know it's not constant. We know it changes depending on how far away you are from the center of the Earth. Key thing is here to remember that R always stands for the center of the Earth. So let's say I have an object, a satellite. Let's say my satellite is here and it's orbiting the Earth. The R that I use is where I'm going to have to include the R, the distances away from the center of the Earth. So what we use is the radius of the Earth. And normally you'll be given this height, the height the satellite is above the Earth. And that height you use there is normally called the altitude. The altitude. So other ways you might see this is way to figure out how do we calculate what that force is. So the way we calculate the force, you can see on our data sheet, is that the force between two masses is equal to G, our universal gravitational constant, mass 1, mass 2, divided by the distance between them squared. Okay, so again, G is our universal constant there, 6.67 times 10 to the negative 11. M is the mass of body 1. So let's say we've got a satellite orbiting the Earth. Mass of body 1 might be the mass of the Earth, and mass of body 2 might be the mass of our satellite. And then in this situation here, that R, the distance between them squared, would be the radius of the Earth there, plus the height that that satellite is above the surface of the Earth, all squared. So what we can see is that our force between two masses, it is directly proportional P-O-R-T-I-O-N, sorry, directly proportional, which I can't spell, but again, what physicists can't spell, directly proportional to the product of their masses, and it's inversely proportional to the square of their separation. So what is the gravitational force? What is the gravitational force? It's directly proportional to the product of their masses and inversely proportional to the square of the separation. And you might all see that then as the inverse square law. So we can clearly see, same for G, it follows the inverse square law. The further away we are, the value of G will drop. So for example, if we double R, G is going to drop by a factor of 4. So again, if we see that, if we double R, G is going to drop by a factor of 4. So again, let's say that's my R there, and this is 4 times R, 2 times R, sorry, we've doubled R. That might be the value of G here, but G is going to get dropped by 4 here, right? Because the further you're away, the lower the value of G. So hopefully you found this video useful, and if you did, just click the link below to sign up to our lessons.